In this video, we're going to be looking at section 1.6 from your book, which includes polynomial functions and rational functions. This video will just talk about polynomial functions. So a polynomial function, as it says in this box, is a function of degree n in the variable x. It's defined as p of x equals a sub n x to the nth power plus a sub n minus 1 x to the n minus 1 plus all the way down to a sub 1 x plus a sub 0, where each a sub I is a real number and a sub n doesn't equal 0 and n is a whole number. So what does that mean? Let's look at these down here as we define it. These are examples of polynomial functions. What the purple box up here basically said was that these numbers that are used as exponents are whole numbers. That's one characteristic. Another characteristic would be that your terms don't have a zero coefficient, but if they do, they simply don't list them, so you don't have to worry about it. Let's look at these definitions. So a sub n is this part right here, and it's the leading coefficient. So it would be defined as the number in front of the highest degree term. Now, the whole term itself is called the leading term, and n here is called the degree of the polynomial. So as we look at these 4 examples or 5 examples of types of polynomials, if you have a constant, that's as if it was saying 3 times x to the 0. So here our degree would be 0, our leading term would be 3, and our leading coefficient is 3. You could write the leading term as 3x to the 0, but you wouldn't have to leave x, you could leave x to the 0 off. That's a unique example. Let's look at a linear function like f of x equals 2/3 x plus 5. Here, the x value, the highest degree we see is 1, so it's a linear function. The whole leading term is 2/3 x, and the leading coefficient is the number in front, so just the 2/3. In a quadratic function, my degree is 2 because the highest exponent is 2. The leading term is 4x squared, and the leading coefficient is just the 4. In f of x, in my cubic function, f of x equals x cubed plus 2x squared plus x minus 5, my degree is 3, leading term is x cubed, and the leading coefficient is understood to be 1. In my quartic function here, starting with a negative x to the 4th minus 1.1 x cubed plus 0.03 or plus 0.3 x squared minus 2x minus 1. The degree is the highest degree, so 4. The leading term would be that negative x to the 4th, and the leading coefficient would be considered to be negative 1. Looking at these, we'll identify some other things about them. Now, if we had the function x squared minus 2x minus 3, which is graphed here, if you factor this, remembering how to factor and set it equal to 0, that will give you this product right here, x plus 1 times x minus 3 equals 0. Using the 0 product rule, if these two things are being multiplied together, giving us an answer 0, we can say that either the x plus 1 equals 0 or the x minus 3 equals 0. In which case, moving my x over, I get x equals a negative 1. Moving my 3 over, I get x equals 3, and that's how we get our zeros. So the zeros are the x values where you're crossing the x-axis. They translate very well to our x-intercepts. So the x-intercepts here would be a negative 1, 0, and 3, 0. The y-intercept is where you're crossing the y-axis here, like we looked at in our last video, and that is negative 3. The relative minimum is negative 4, so that's the y-coordinate that is the lowest point on my parabola. It occurs when x equals 1. There is no relative maximum because these parabolas keep going onwards to positive infinity. My domain is all real numbers because my parabola goes all the way to the left. to negative infinity and all the way to the right to positive infinity as it continues. The range is the y values that this parabola takes on, and the parabola has a lowest y value at -4, but then continues to go to positive infinity. So my range is -4 to infinity. If we look at our next graph, we have a cubic function that looks kind of like a curvy N here. And we've identified all the points here. This is the function g of x equals x cubed plus 2x squared minus 11x minus 12. If you were to factor this, you would get it to factor to x plus 4 times x plus 1 times x minus 3. That yields the zeros of a -4, a -1, and a +3. So those are our x-intercepts here. Our y-intercept, of course, is this constant out by itself, so -12. And the relative minimum would be, see, we have more minimums that go further down here, but we have a minimum locally at -20.745. It occurs when x is about 1.4. Our relative maximum, similarly, is here. It is the maximum in this vicinity. We get higher maximums going over here, but our relative maximum is the 12.597. It's the y value, and that's when x is about 2.7. Our domain is all real numbers because x keeps going to the left and to the right. And since this curve has negative values all the way to negative infinity and positive values all the way to positive infinity, its range is negative infinity to positive infinity. So let's look at some examples of polynomials. In our first example, we have a quadratic function that opens upward of the form x squared plus 3x plus 1. In our second example, we just have a linear function, which is the constant f of x equals -3. In our third example, we have a cubic function, this curvy one, where it approaches negative infinity from the left and positive infinity as you go to the right. And here we have a quartic function, a fourth degree function, which opens downward and has end behavior where both ends of your curve approach negative infinity. All right, let's look at what we define as end behavior of a function. When we talk about end behavior, we're talking about what happens when x approaches negative infinity or positive infinity. So the end behavior of a polynomial function is determined by the degree n and the sign of the leading coefficient, as indicated in the following graphs. So if p, your function polynomial, has an odd degree, what happens is the ends of the graph go in opposite directions. So here, these first two graphs have the ends go in opposite directions. So what that means is over here, as x is going to the left, approaching negative infinity, my y value is approaching negative infinity. That's what this says. And here, as x goes to the right, as x is approaching positive infinity, the y value approaches positive infinity. So they're going in opposite directions. This happens when the lead coefficient of an odd degree function is positive. So it's going to start low and end high. If the leading coefficient is negative, then as x approaches negative infinity, the y is approaching positive infinity. And as x approaches positive infinity, the y value is approaching negative. Now, if you have an even degree function, like if you had y equals x to the 4th, if it was a positive x to the 4th, then both of the ends of your curve would approach positive infinity. So as x approaches negative infinity, the y value is approaching positive infinity, whereas x approaches positive infinity, the y value is approaching positive infinity also. This is if the lead coefficient is positive. Conversely, if the lead coefficient is negative, then both the y values approach negative infinity, either when x is going to negative infinity or positive infinity. So that's what that means. So basically, to summarize, If you have an odd degree function, the ends of your graph go in opposite directions. If you have an even degree function, like x to the fourth, then both ends of your graph go in the same direction. And then depending on whether your lead coefficient is positive or negative, if it's positive, it's mostly an increasing function. If it's negative and odd degreed, it's mostly a decreasing function. If the lead coefficient is positive on an even degree function, both ends go up. If the lead coefficient is negative on an even powered function, then both ends of your graph approach negative infinity. Now, just using that information only, let's see if we can match these graphs in example 1. Here we have a 4-3 function, so it's even. So on our even functions back here, both ends go the same direction. So let's see, and the lead coefficient is positive. So which one could this be? If you said C, you are correct, because it has a positive lead coefficient and the degree is even, both ends are going to go up, it's got to be C. So for this example, our graph is C. In this one, again, we have an even degree function, but our lead coefficient is negative. So that's like this last example here. So that's got to be A. Both ends go in the same direction, but they go downward because the lead coefficient is negative. If we look here, we have an odd degree function with a positive coefficient. So since it's got a positive coefficient and it's odd degree, both ends go in opposite direction, but it's mostly an increasing function. So this one has to be B. H of x has to be the graph B. Finally, K of x has an odd degree function, so the ends go in opposite directions, and the lead coefficient is negative. So since the lead coefficient is negative, it's mostly a decreasing function and opposite directions. So this one has to be D. Kind of how we match it up. In example 2, it says, consider the function p of x equals x cubed plus x squared minus 17x plus 15. Determine whether each of the numbers 2 and negative 5 is a 0 of the polynomial. So a 0 of the polynomial, what that means is, well, first off, it's where the function crosses the x-axis. Those are defined as zeros. Now, what happens when a function crosses the x-axis is the y value equals 0. So to determine whether these numbers are zeros, what we do is we substitute them into this equation. And if the answer equals 0, then their y value is 0, and they would be considered zeros of p of x. So let's do that. Let's pause the video and you see what you think on those. Plugging in 2, we would get a y value of -7. So that means 2 is not a 0. Substituting in -5, we get 0. So we can say that x equals -5 is a 0 of this function. Looking at example 3, another way we can find zeros is by factoring it. So this function is already factored. And to find the zeros, then we set it equal to 0. Now, if I set this equation equal to 0, I know that 5 doesn't equal 0. But maybe this x minus 2 equals 0. Or maybe this x plus 1 equals 0. In that case, we would solve this by adding 2 to both sides and get x equals 2. That would be one of our zeros. And here we'd subtract 1 from both sides and get x equals -1. So those would be our 2 zeros for this function. Similarly, in example 4, we have a function g of x, which is defined in factored form by a negative x plus x minus 1 times x minus 1 times x plus 2 times x plus 2. Setting this equal to 0 would once again yield that either the x minus 1 equals 0 or the x plus 2 equals 0. Solving this, we would add 1 to both sides and get x equals 1, or subtract 2 from both sides to get x equals a -2, and those would be our zeros of our function g of x. Let's go back to trying to match some of these equations with graphs. So in problems 9 through 14, we're trying to identify which graph matches which equation. So take a moment and let's try to find problem 9 and 10. Then we'll look at them together. Here we can see in problem 9, f of x equals negative x cubed minus x squared plus 2x, that we have an odd degree function, and in an odd degree function, the ends of the function go in opposite directions, the end behaviors, and we have a negative lead coefficient, meaning that over most of its domain, it's going to be a decreasing function. Sorry about that phone alert. So it's a decreasing function mostly with the ends going in opposite directions, so that's got to be f, where we have a curve that mostly is decreasing and the ends go in opposite directions. On 10, similar once again, we have an odd degree function, so the ends go in opposite direction, but a positive lead coefficient, so it's mostly going to be increasing. So that's got to be this one. The ends go in opposite direction. Mostly it's an increasing function, so that is D. Let's have you match the rest of these and we'll see what we get. Pause the video and give it a try. In matching the rest of these, you'll notice on 11, you have a negative lead coefficient with an even exponent, meaning that it opens downward. But since its exponent is 4, it may not be just a parabola. It could have a couple of lumps in it, so we know that number 11 actually matches with E. So we've got this whole bottom row matched. If we look at 12, we have another even function with a negative lead coefficient, but we know that's a quadratic because we looked at those in section 1.5. So that's got to be A. If we look at 13, we have another quadratic, but it's got a positive lead coefficient, so it opens upward. That's got to be C. And finally, here we have a 4th degree polynomial, so both end behaviors go in the same direction, and it's got a positive lead coefficient, so that's got to be B, like that. All right, I hope these were helpful. In our next video, we are going to look at rational functions. Thanks for watching.